Hello, class. Alright, so this lecture is going to be on something called moles, where we're going to look at matter on kind of like a small scale, like what's going on at an atomic level, trying to connect that to what's going on a macroscopic level, like the larger quantities. If we have a gas, we're going to have like, the macroscopic quantities would be things readily observable, like pressure and volume. Microscopic quantities would be like the number of atoms or the number of molecules, like the average kinetic energy of the molecules. So let's start out with some very basics. Just talk about atoms. So an atom, we have a nucleus that contains protons and neutrons. And then outside the nucleus, we have electrons. And that's basically it. You can go into more detail about what's going on inside the nucleus and all that, but for our purposes, this is fine. Now, atoms are incredibly tiny. Let's look at the mass of these. So mass of a proton, mass of a neutron, and mass of an electron. So I have to look these values up because we have to go to several significant figures to even notice a difference between a proton and a neutron. So usually I just remember 1.67. And the electron, I guess if we want significant figures. Now these are incredibly tiny numbers. Now this is like you have like 26 zeros and then a 167 kilograms. So what that means is that ordinary matter contains an enormous number of atoms. Okay. So if we look at like a single atom, mass of an electron, very tiny compared to protons and neutrons. So to a good estimate, the mass of an atom, we can almost disregard the electrons. To a round number, we can say the mass of an atom is approximately equal to, I'm just going to write this equation. N times U, where N is the number of nucleons Nucleons are the protons and neutrons. They exist in the nucleus of the atom. And U is something called an atomic mass unit. So again, this is kind of a rough estimate of the mass of any atom. You just count, like, say you have 6 protons, 6 neutrons. So you have 12 nucleons, multiply that by an atomic mass unit. And an atomic mass unit is roughly equal to the mass of a proton or the mass of a neutron. I'll write down the value right now. This is 1.6605 times 10 to the minus 27 kilograms. Now, this number might surprise you. Because I said this is basically the mass of a proton or a neutron. But if you look at it, it's actually a little bit less than either a proton or a neutron. So how does that make sense? And the answer is one of those famous equations in physics, E equals mc squared. This is Einstein's famous equation, or one of them, where that's energy, m is mass, c is the speed of light. And this kind of destroyed this idea. Before Einstein, there was this idea of conservation of matter, that matter is always conserved. Mass was always conserved. But now we see that mass and energy can be interchanged. So mass is just a form of energy. And so there's a discrepancy between like the mass of a proton, mass of a neutron, and the mass, or an atomic mass unit. And the reason why is these are free particles, like the mass of a proton. This is just an isolated proton by itself. And, but when you look in the nucleus of an atom, there are forces involved. There's energy involved in the nucleus of an atom that has to be taken into account. And an example would be, say you have two masses. Let's look at a gravitational example. Say you have two large objects. So in one case, you have two massive objects right next to each other. And here you have two massive objects that are separated by a significant difference. There's more energy here because if they're attracted to each other, they can accelerate towards each other, gain this kinetic energy. So they have more potential energy here. So again, these like an isolated proton has more energy than it does inside the nucleus of an atom, and that's why this atomic mass unit is smaller than these individual masses. Ultimately, it comes down to that equation, that energy, or matter is basically a form of energy. Okay, but now, how is this number defined? Well, the precise definition is, let me just erase everything. We'll just write down the atomic mass unit. Usually I just go 1.66. Yeah, I was writing down more significant figures earlier, just to you need to in order to see if there's any difference at all between like a proton and a neutron. But that's usually good enough for our purposes. Okay, and how is an atomic mass unit defined? Well, there's a certain atom called carbon-12. Now, what is it? Okay, so if you look at a periodic table, you look at, say, carbon. That's got this number 6. You might see different ways. It might look something like this. Actually, it's probably not going to be exactly 12. It'll be 12 point something. And so, again, this number is the atomic number. By definition, that is the number of protons. So any atom that has 6 protons is carbon, just by definition. So this is atomic number. And this number here is atomic mass. Okay, now I said carbon-12. Why 12? Well, turns out there's different isotopes of carbon, and every element has different isotopes. And so if you look at carbon, you have carbon-12, carbon-13, and carbon-14. These are definitely the main 3. There might be others, but I'm not even sure if there are. But anyways, these are the main isotopes of carbon. And carbon-12, these are like the atomic masses. This would be 6 protons and 6 neutrons. This would be 6 protons, 7 neutrons. And here we have 6 protons and 8 neutrons. And so, like normal carbon, if you just have like a sample of carbon, like say coal or a diamond, different atoms might have different number of neutrons. Most of them are going to be carbon-12, but a small percentage will be 13 and 14. And so the way atomic mass is defined, they picked carbon, probably because it's one of the most important elements for, it's kind of the foundation of all life. So I'm guessing that's why they picked carbon to define the atomic mass unit. But we have to take this particular isotope of carbon. So carbon-12, an atom with 6 protons and 6 neutrons. And by definition, the atomic mass would be 12 atomic mass units. So the atomic mass of this atom is by definition 12 atomic mass units. And then we can find out just by measurement what an atomic mass unit is. Okay. Now, where are we going to go with this? Say we have carbon 12. And say we have 12 grams of carbon 12. So if we have exactly 12 grams of carbon 12, how many atoms do we have? And the answer to that is something called Avogadro's number. Now I'm going to write it like this. 6.02 times 10 to the 23rd per mole. We haven't talked about what moles are yet, but we'll get to that in a moment. So here, I'll put that over here. So remember, 12 grams is not very much. I think like a nickel is 5 grams. So if you had like a little more than 2 nickels, like that amount of carbon, you'd have this many atoms. So that is this is an enormous number. If you wanted to count a number like this, well, basically you couldn't. This number is too high. Even if you spent your entire life, you would never be able to count to a number this high. So atoms are enormous. Kind of a good rule of thumb, something worth memorizing. I don't really recommend memorizing too much. But just to put things in perspective, the number of seconds in a year is around 3 times 10 to the 7th power. It's supposed to be an approximately equal to symbol there. So 3 times 10 to the 7th power, that's 30 million. That's actually a pretty big number. Doesn't look that big, but it is. And so this is approximately true. It's actually kind of a nice, a little more accurate. You could say pi times 10 to the 7th. It's more like 3.1 something, but yeah, so if you wanted to count a number like this, a good way to think of it is you could count at a rate of 1 per second. It would take you, well, let's see, the number of years that it would take you. So like the number that you count would be like the rate that you count times the time. So the time to count a number like this, divide by the rate, that would be 3 times 10 to the 7th. 2 times 10 to the 16th power. That's how many years it would take you to count the number of atoms in like 12 grams of carbon. It would take you this many years if you did nothing but count at a rate of 1 per second. So 10 to the 16, that's 10 million billion years. Way beyond the age of the universe. Not even close. The universe is, what is it, like 14 billion years or something? This is millions of billions of years. It's, so yeah, I mean, numbers like this are absolutely enormous. Hard to really wrap your mind around it. But let's get to the subject of moles. I'm going to read the kind of a precise definition. It's also called the gram mole. It says 1 gram mole of a substance contains as many particles as there are atoms of 12 grams, or atoms in 12 grams of carbon 12. Okay, so 1 gram mole. So again, you could have 1 mole of anything. 1 mole of anything contains this many particles. So 1 mole of carbon-12 atoms contains, this many particles. Like 1 mole of pennies would contain this many pennies. You could, it's just a number. Okay, so how do we use this? I have an example. See, maybe I always thought it would be more convenient if we just use hydrogen to define, like a mole or something. But they use carbon, and we're stuck with that. But I kind of like comparing it to hydrogen, because hydrogen is basically an atomic mass of 1. Okay, so as an example, let's say we have 240 grams of CO2. We want to know, like, how many moles and how many molecules. So, let's see. Let's line up some atoms of carbon-12. So let's say we have carbon-12. And we have 6.02 times 10 to the 23rd atoms of carbon-12. So we know this would have a mass of 12 grams. And now, as an intermediate step, let's say we have an equal number of hydrogen atoms. What would the mass of this many hydrogen atoms be? Well, every hydrogen atom is 1/12 the mass of a carbon-12 atom, roughly. Rounding off a little bit, but roughly 1/12 the mass. We have the same number, so we'd have 1/12 the mass overall. So basically, 1 Avogadro's number worth of hydrogen atoms would have a mass of 1 gram. Now let's get to carbon dioxide. Here we have this molecule. We'll draw it like this, like carbon and 2 oxygen. And again, we have this number of molecules of carbon dioxide. So how much does 1 molecule of carbon dioxide weigh? Or what is the mass? So carbon has a mass of 12. Oxygen has a mass of 16. So if you combine that, CO2, that would be 32 plus 12, that would be 44. And so a single molecule of carbon dioxide is 44 times as massive as a single atom of hydrogen. So we know the mass of carbon dioxide. This many particles of carbon dioxide would have a mass of 44 grams. And so again, if we look at a periodic table, I'm not sure if I have one with me or not. I think I have an... that's all right though. Okay, so I don't have a periodic table, but let's say we look at a periodic table. On this pick, let's say nitrogen. It's going to look something like this. So again, this is the atomic number. And this here is the atomic mass. So what does this atomic mass mean? Like, what are the units here? Well, there's two ways we can look at this. For nitrogen, it has an atomic mass of 14. So we can say one nitrogen atom has a mass of 14 atomic mass units. Or we can say one mole of nitrogen has a mass of 14 grams. So if we're talking about a single atom, that would be its mass. This would be its mass in atomic mass units. If we're looking at a mole, so again, if we have 6.02 times 10 to the 23rd atoms of nitrogen, it would have a mass of 14 grams. So the atomic mass, you can look at it either on an atomic level, the microscopic level, in terms of atomic mass units, or the macroscopic level, looking at moles. So, yeah, let's come back to this question of carbon dioxide. So we have 240 grams. Let's start with CO2. Again, carbon, I already did this, but I erased it. That'd be 12. Oxygen is 16. And again, you look these up in a periodic table. So CO2, we'd have 2 oxygen, that's 32, plus 1 carbon, which is 12, so that'd be 44. So we know 1 mole of carbon dioxide has an atomic, or has a mass of 44 grams. So 1 mole of CO2 equals 44 grams. So we can use this conversion factor. We have 240 grams of CO2, and then we can say 44 grams per mole of CO2. And I realize I just did this backwards. Technically not wrong, but not what we're looking for. Yeah, we have 1 mole carbon dioxide would be 44 grams. So I usually don't write this CO2. Let me rewrite that just with the, we have 240 grams. And we know 1 mole is 44 grams. So the number of moles, we use a lowercase n for moles. So this would be 240 divided by 44. I don't know if I wrote that down. Let's see, 240 divided by 40 would be 6. This will be a little bit less. Let's say around 5.8. And we use MOL for mole, a little shorthand. So yeah, lowercase n is the number of moles, and an uppercase n would be the number of atoms or molecules, just in general, the number of particles. So now we want to know how many molecules are there. Let me just check this number, 44 times 5.8. Let me see how close that is. That's a bit high. So maybe around 5.7 would have been better. Sorry, I don't have a calculator. That's a little bit high, but close. Maybe around 250. I think 5.6 might be better. Let's go with that. Okay, so we have around 5.6 moles. And then the number of particles we have 5.6 moles, and we just multiply by Avogadro's number. So the moles cancel. So 5.6 times 6.02, just going to round off a little bit. We end up with 33.6 times 10 to the 23rd power. Let's say around 3.4 times 10 to the 24th power. So that would be the number of molecules in 240 grams of carbon dioxide. And again, you can do this for anything, any like atom or molecule. And this is one of those things where if you've had chemistry, you probably already know this. And most people have had chemistry, but this might be new for some of you. So there's a few examples in the notes, but that's the basic procedure. Maybe we'll do one more. Yeah, let's just do one more problem. But if this is new for you, this is definitely the kind of thing you want to practice. Just do several problems. It's not hard once you get the idea. Okay, here's an example from the book. How many molecules in 121 grams of nitrogen gas? So like, how many molecules? Now, I wanted to do this example because something you could easily overlook. It's how many molecules, that's a key word there, and another key word, nitrogen gas. So again, if you have a gas of nitrogen, they form, the nitrogen atoms bond with each other. And so we're talking about molecules, not atoms. Typically, that's what happens. Things like helium and neon are different. They're noble gases. They don't react with anything. But, yeah, nitrogen gas, that would be diatomic. Okay, so we've got nitrogen atom would be like around 14 on the periodic table. So we know 1 mole of N2 would be 28 grams. So we have 2 atoms, each has a mass of 14. So like 1 molecule of nitrogen gas would have a mass of 28 atomic mass units. 1 mole would have a mass of 28 grams. So now that we've got that here, we have 121 grams. So we want to find, let's start with the number of moles. So we have 121 grams, and then 1 mole is 28 grams. So that's going to be around 4, oh, I have this one actually. No, I don't. I just have the number of. So it's going to be around 4 point something. Sorry, I really should just get a calculator for this. I make up problems a lot without. This one's in the notes, but the question is how many molecules, so I didn't bother with this intermediate step. That's close enough. 118, 121. Happy with that. Okay, so around 4.2 moles. And then the number of molecules, 4.2 moles times 6.02 times 10 to the 23rd per mole. So to get the number of molecules, if you have the number of moles, you just multiply by Avogadro's number. So here, 24, 25 something. Yeah, let's see. Yeah, around 25 times 10 to the 23rd power. Or 2.5 times 10 to the 24th power. Okay, so it's a very important topic because it allows us, if we have like a finite sample of something, like something, macroscopic, large scale, something we'd measure in grams, this will tell us like how many molecules there are. And again, this Avogadro's number, that is an enormous number. It's the number of stars in a typical galaxy like the Milky Way is around 10 to the 22nd power. So basically what that means, if you have a glass of water, there's more molecules in that glass of water than there are stars in the Milky Way galaxy. So again, that's a huge, huge number, which means atoms are extremely small. So again, I think this is probably a review for most of you, but if this is new, then definitely practice doing things with problems like this. Like if you have a sample of something, it could be anything in the periodic table, just an element, or you can make molecules. And then just find out like how many atoms or how many moles there are. It's kind of a fun problem you can do. Try to figure out how many atoms there are in the universe. You don't need to know all that much to figure that out either, to approximate it anyways. Basically what you need to know, a few things. There's about 100 billion galaxies in the known universe, and each galaxy has around 100 billion stars. And if you use our sun as a guide, the mass of the sun in grams is about 2 times 10 to the 33rd power in grams. And if you just put all that together with Avogadro's number, you can figure out approximately how many atoms there are in the universe. I'll actually leave that one instead of working it out. If any of you want to figure that out, definitely worth doing. So yeah, it doesn't take too much to know. And again, we're assuming that all the mass in the universe is in the form of stars, which is not true, but to a rough estimate, it's not bad. Most of the mass is, at least for visible matter. You might have heard of something called dark matter, dark energy. We have no idea what those are, but even if you consider that, they say like the visible matter, there's like 10 times as much dark matter as visible matter. That would just be an exponent of 1 anyway, so you get pretty close just by ignoring that entirely. All right, so that'll be it for this lecture.